High dynamic range imaging is a high dynamic range technique used in imaging and photography to reproduce a greater dynamic range of luminosity than is possible with standard digital imaging or photographic techniques. The aim is to present a similar range of luminance to that experienced through the human visual system. The human eye, through adaptation of the iris and other methods, adjusts constantly for the broad range of luminance present in the environment. The brain continuously interprets this information so that a viewer can see in a wide range of light conditions. HDR images can represent a greater range of luminance levels than can be achieved using more traditional methods, such as many real-world scenes containing very bright, direct sunlight to extreme shade, or very faint nebulae. This is often achieved by capturing and then combining several different narrower range exposures of the same subject matter. Non-HDR cameras take photographs with a limited exposure range, resulting in the loss of detail in highlights or shadows. The two primary types of HDR images are computer renderings and images resulting from merging multiple low dynamic range or standard dynamic range photographs. HDR images can also be acquired using special image sensors, like an oversampled binary image sensor. Due to the limitations of printing and display contrast, acquiring an HDR image is only half the story. One must also develop methods of displaying the results. The method of rendering an HDR image to a standard monitor or printing device is called tone mapping. This method reduces the overall contrast of an HDR image to facilitate display on devices or printouts with lower dynamic range, and can be applied to produce images with preserved or exaggerated local contrast for artistic effect. HDR lenses are currently being developed by Ricoh Imaging. Current applications include prototype lenses being trialed on the International Space Station. Further developments include consumer lenses for use in low-light conditions such as night driving. These HDR lenses combine a laminate of borosilicate carbide and polarizing films to actively refine the intensity of various wavelengths of light, which results in a higher dynamic range image seen by the eye. Photography. In photography, dynamic range is measured in exposure value differences. An increase of 1 eV or 1 stop represents a doubling of the amount of light. Conversely, a decrease of 1 eV represents a halving of the amount of light. To reveal detail in the darkest shadow requires high exposures. Inversely, to prevent bleaching out of detail in very bright areas, one must choose very low exposures. Most cameras cannot provide this range of exposure values within a single exposure, due to the low dynamic range. High dynamic range photographs are generally achieved by capturing multiple standard exposure images, often using exposure bracketing, and then later merging them into a single HDR image. Digital images are often encoded in a camera's raw image format. Because 8-bit JPEG encoding doesn't offer a great enough range of values to allow fine transitions, any camera that allows manual exposure control can make images for HDR work, although one equipped with auto exposure bracketing is far better suited. Images from film cameras are less suitable as they often must be digitized first, so that they can later be processed using software HDR methods. In most imaging devices, the degree of exposure to light applied to the active element can be altered in one of two ways, by either increasing or decreasing the size of the aperture or by decreasing the time of each exposure. Exposure variation in an HDR set is only done by altering the exposure time and not the aperture size. This is because altering the aperture size also affects the depth of field, and so the resultant multiple images would be quite different, preventing the final combination into a single HDR image. An important limitation for HDR photography is that any movement movement between successive images will impede or prevent success in combining them afterwards. Also, as one must create several images to obtain the desired luminance range. Such a full set of images takes extra time. HDR photographers have developed calculation methods and techniques to partially overcome these problems, but the use of a sturdy tripod at least is advised. Some cameras have an auto-exposure bracketing feature with a far greater dynamic range than others, from the 3 EV of the Canon EOS 40D to the 18 EV of the Canon EOS 1D Mark II. As the popularity of this imaging method grows, several camera manufacturers are now offering built-in HDR features. For example, the Pentax K7 DSLR has an HDR mode that captures an HDR image and outputs a tone-mapped JPEG file. The Canon PowerShot G12, Canon PowerShot S95 and Canon PowerShot S100 offer similar features in a smaller format. Some smartphones provide HDR modes, and most mobile platforms have apps that provide HDR picture taking. Camera characteristics such as gamma curves, sensor resolution, noise, photometric calibration and color calibration affect resulting high dynamic range images. Color film negatives and slides consist of multiple film layers that respond to light differently. As a consequence, transparent originals feature a very high dynamic range. Tone mapping reduces the dynamic range, or contrast ratio, of an entire image while retaining localized contrast. Although it is a distinct operation, tone mapping is often applied to HDRI files by the same software package. Several software applications are available on the PC, Mac and Linux platforms for producing HDR files and tone-mapped images. Notable titles include comparison with traditional digital images. Information stored in high dynamic range images typically corresponds to the physical values of luminance or radiance that can be observed in the real world. This is different from traditional digital images, which represent colors that should appear on a monitor or a paper print. Therefore, HDR image formats are often called scene-referred, in contrast to traditional digital images, which are device-referred or output-referred. Furthermore, traditional images are usually encoded for the human visual system, which is usually called gamma encoding or gamma correction. The values stored for HDR images are often gamma compressed or logarithmically encoded, or floating point linear values. Since fixed point linear encodings are increasingly inefficient over higher dynamic ranges, HDR images often don't use fixed ranges per color channel, other than for traditional images, to represent many more colors over a much wider dynamic range. For that purpose, they don't use integer values to represent the single color channels, but instead use a floating point representation, common are 16-bit to 32-bit floating point numbers to represent HDR pixels. However, when the appropriate transfer function is used, HDR pixels for some applications can be represented with as few as 10 to 12 bits for luminance and 8 bits for chrominance without introducing any visible quantization artifacts. History of HDR photography. Mid-19th century, the idea of using several exposures to fix a too extreme range of luminance was pioneered as early as the 1850s by Gustave Le Gray to render seascapes showing both the sky and the sea. Such rendering was impossible at the time using standard methods, the luminosity range being too extreme. Le Gray used one negative for the sky and another another one with a longer exposure for the sea, and combined the two into one picture in positive. Mid-20th century manual tone mapping was accomplished by dodging and burning, selectively increasing or decreasing the exposure of regions of the photograph to yield better tonality reproduction. This is effective because the dynamic range of the negative is significantly higher than would be available on the finished positive paper print, when that is exposed via the negative in a uniform manner. An excellent example is the photograph Schweitzer at the Lamp by W. Eugene Smith, from his 1954 photo essay A Man of Mercy on Dr. Albert Schweitzer and his humanitarian work in French Equatorial Africa. The image took 5 days to reproduce the tonal range of the scene, which ranges from a bright lamp to a dark shadow. Ansel Adams elevated dodging and burning to an art form. Many of his famous prints were manipulated in the darkroom with these two methods. Adams wrote a comprehensive book on producing prints called The Print, which prominently features dodging and burning. In the context of his zone system, with the advent of color photography, tone mapping in the darkroom was no longer possible due to the specific timing needed during the developing process of color film. Photographers looked to film manufacturers to design new film stocks with improved response, or continued to shoot in black and white to use tone mapping methods. Color film capable of directly recording high dynamic range images was developed by Charles Wyckoff and E.G. and AMP-G in the course of a contract with the Department of the Air Force. This XR film had 3 emulsion layers, an upper layer having an Asher speed rating of 400, a middle layer with an intermediate rating, and a lower layer with an Asher rating of 0.004. The film was processed in a manner similar to color films, and each layer produced a different color. The dynamic range of this extended range film has been estimated as 1 to 108. It has been used to photograph nuclear explosions, for astronomical photography, for spectrographic research, and for medical imaging. Wyckoff's detailed pictures of nuclear explosions appeared on the cover of Life magazine in the mid-1950s. Late 20th century, the concept of neighborhood tone mapping was applied to video cameras by a group from the Technion in Israel led by Dr. Oliver Hilsenrath and Professor Y.Y.Zevi, who filed for a patent on this concept in 1988. In 1993, the first commercial medical camera was introduced that performed real-time capturing of multiple images with different exposures, and producing an HDR video image by the same group. Modern HDR imaging uses a completely different approach, based on making a high dynamic range luminance or light map using only global image operations, and then tone mapping this result. Global HDR was first introduced in 1993, resulting in a mathematical theory of differently exposed pictures of the same subject matter that was published in 1995 by Steve Mann and Rosalind Picard. On October 28, 1998, Bencero created one of the first nighttime HDR plus G of SDS-95 on the launch pad at NASA's Kennedy Space Center. It consisted of 4 film images of the shuttle at night in that were digitally composited with additional digital graphic elements. The image was first exhibited at NASA headquarters Great Hall, Washington, D.C. in 1999 and then published in Hasselblad Forum, Issue 3 1993, Volume 35 ISSN 0282-5449. The advent of consumer digital cameras produced a new demand for HDR imaging to improve the light response of digital camera senses, which had a much smaller dynamic range than film. Steve Mann developed and patented the global HDR method for producing digital images having extended dynamic range at the MIT Media Laboratory. Mann's method involved a two-step procedure: generate one floating-point image array by global-only image operations, and then convert this image array, using local neighborhood processing, into an HDR image. The image array generated by the first step of Mann's process is called a light space image, light space picture, or radiance map. Another benefit of global HDR imaging is that it provides access to the intermediate light irradiance map, which has been used for computer vision and other image processing operations. In 2005, Adobe Systems introduced several new features in Photoshop CS2, including merge to HDR, 32-bit floating-point image support, and HDR tone mapping. Example: this is an example of 4 standard dynamic range images that are combined to produce 2 resulting tone-mapped images. Original images HDR senses. Modern CMOS image sensors can often capture a high dynamic range from a single exposure. The wide dynamic range of the captured image is non-linearly compressed into a smaller dynamic range electronic representation. However, with proper processing, the information from a single exposure can be used to create a HDR image. Such HDR imaging is used in extreme dynamic range applications like welding or automotive work. Some other cameras designed for use in security applications can automatically provide 2 or more images for each frame, with changing exposure. For example, a sensor for 30 fps video will give out 60 fps with the odd frames at a short exposure time and the even frames at a longer exposure time. Some of the sensor may even combine the 2 images on chip so that a wider dynamic range without in-pixel compression is directly available to the user for display processing.